Welcome to Day 2, Free Body Diagrams, the sequel. For each of the demonstrations we're going to do, you will watch the demonstration, pause the video, draw the free body diagram, and then I'll walk you through the correct answer. Let's get started. Let's go back to what we ended class with yesterday and look at the green ball hitting the beach ball and draw the free body diagram of the beach ball. Here's the demo. Don't you love that super slow motion? Now it's your turn to draw the free body diagram of the beach ball, and then we'll come back and I'll show you the answer. So let's draw our free body diagram. We start with the beach ball, and then we're going to temporarily add the little green ball just to show the context. But of course, since we're drawing the free body diagram on the beach ball, we don't want the little green ball, so we'll take it out. Now, the major force, the one we see most of all, is that there's an impact force from the green ball hitting the beach ball, and that impact force is to the left. Then, of course, we still have the weight of the beach ball trying to pull the beach ball down, so we'll add that. And then the last force, which we sometimes forget, is that the beach ball is hanging from the ceiling by a thread. So there's a tension force that is pulling upward on the beach ball and is keeping the beach ball from falling. But we want to make sure we don't automatically put four forces on the diagram, because in this case there is no rightward force or backward force on the beach ball. So let's check our answer. Yeah, we did pretty well. We've got impact, weight, and tension. And the tension and weight forces are equal and opposite, so they're going to cancel out. So B plus C equals 0. But notice that impact arrow, there's nothing to balance it. It's all by itself. So if we add all three forces up, now it's not 0, and in fact the beach ball, as we saw in the video, is going to move to the left. All right, let's try another one. I'm going to fill just an ordinary drinking glass with water up to overflowing, and then I'm going to take a Coke can, stuff it in the top of the glass, and I'm going to flip it over, and you're going to watch the motion of the can. As the water drains out, the can falls upward. What's with that? Now let's draw a free body diagram of the can. So let's draw that free body diagram. We're just going to draw the can, not the glass or the water, because it's what? A free body diagram of the can. So we know the can is moving up, and that's going to actually affect our free body diagram. We should be thinking about that. Now, the easiest force to add to our free body diagram is the weight. We know the weight is pulling the can down. But what the heck is pulling the can upward? We know it has to be there, so let's just draw it for now. We know what the arrow has to look like. It has to be attached to the can, it has to be pointed up, and it has to be longer than the weight arrow. But we still don't know what it is. But we do know what it does. We know that arrow A, whatever it is greater than the weight. That's for sure. Well, just to fill you in, that force is actually produced by the air pressure pushing all around the can and pushing it up into the glass. There, mystery solved. One more free body diagram to do. Okay, this one is about as simple as it gets. There's a glass cylinder filled with shampoo, and we're going to drop a steel marble in it. Watch what happens. Wow. Now that makes for an exciting video. Done! So let's draw that free body diagram of the marble. So it's just the marble, no cylinder. And we know we have our old friend weight pulling the marble downward. That's not a problem. But let's think about where the marble is. It's dropping through some fluid. And we remember from the Introduction to Force lab that when you do that, there's a frictional force called drag. And in this case, the drag, like all friction, is trying to oppose the motion and slows the marble down. Nonetheless, even with the drag, the marble still goes down through the tube. So now we expect that the forces are not equal to each other. In fact, if we have drag as force A and weight as force B, it looks like force B, the weight, is bigger than the drag. And in fact, we can be really confident of that because we see the marble moving down. Too bad we're really wrong. But don't feel bad. Everybody else was wrong for over 2,000 years until Galileo finally realized there was a problem with how we thought about forces and movement. And we'll get to that with a little Hot Wheels demo on Thursday or Friday. See you then.